So Felipe is at Sophos. He's a data scientist. He's been working on deep and adversarial machine learning. He's come out of NYU. He's been at Sophos for about 2.5 years now. And he's a machine learning engineer. Have I got that right? So away you go, talking about describing malware via tagging.
Hello, thank you, Sarah, for the introduction.
Oh, I forgot a bit. Also, this is like freestyle. You can ask questions during his talk.
Yes, so feel free to interrupt during the conversation. This is work we did at Sophos AI in collaboration with Ethan Root, Alex Long, Tad Hapner, and Konstantin Berlin. It's a problem that I've been interested in for some time already, which is, all right, we know that we can train deep neural networks to identify malicious from benign samples. Now the question is, can we go one step further and not only report if something is malicious, benign, and a confidence score, but also try to explain what kind of maliciousness we've found in the binary file. So I want not only to say, okay, this is a malicious sample, but maybe this is ransomware, or this is spyware, or more information about it that can help the consumer of that data to identify possible remediations and see how to go about the attack that is underway. How the industry talks about malware description. The gold standard for malware description today is the MIC framework. It has been developed by the MITRE Corporation, and it's a structured language that encodes very high fidelity attributes about malware samples. This goes very deep into things like what kind of obfuscation methods does the malware use, what kind of privilege escalation techniques does it use, etc. So it's very, again, high fidelity and very fine-grained information about a given malware sample. It's something that very difficult to extract automatically, so you need generally a group of people looking at this malware sample in different views, in dynamic analysis, static analysis, etc., to come with a report of these characteristics. So unfortunately, even though this is the best information we could get our hands in, building a data set of malware samples that have this information, it would be very expensive to come about. The other way that the industry goes about describing malware is by giving us detection names whenever they find something that is suspicious or is malicious. They would say, okay, we found something malicious here, and this is the name that we're assigning to it. Within that name, there is usually expert information embedded, so there was someone that wrote a signature that matches to that detection name particularly, and they're trying to give us further information about the kind of malicious code that has been found. This is an example for one particular malware sample. These are all the names that 10 different antivirus solutions gave to the same particular sample, and if we look and we read between lines, I mean, any of these is super informative alone, but if we look at those in a transversal way, we start finding that there is more information that meets the eye in the first place. So there is a bunch of information and tokens embedded in those families that tells us that this is potentially a ransomware sample, but if we look further, there is this big ransom token that tells us that it's potentially a file infector. So it's a specific kind of ransomware. And there is information from one of those vendors that didn't identify the sample as malicious, but identifies the sample as being packed with a particular packer. So one way that we can try to describe malware is by extracting information from these families from different detection vendors and abstracting them into higher level categories. So this is somewhere in the middle between what MITRE is doing by looking at very fine-grained details and the family names that, if we look at them alone, they have been developed independently by anti-malware companies. They don't line up very well, but if we look across them, we can extract important information. So one experiment that we run is, okay, we defined 11 different tags that are interesting to us and things that we might want to extract from malware samples. So we have we've defined these tags: packed, spyware, dropper, worm, file infector, downloader, adware, installer, ransomware, crypto miner, and floater. I'm not going to get into them in particular, but I think they're pretty self-explanatory on what they're trying to see. Within spyware, we put things that are related with backdoors and password stealers, etc. So the proposal is to try to learn those tags directly from the from the binary files, and without running those files in a dynamic way. They convey different kinds of information, purpose, sometimes are related with families, characteristics, and they're related with detection names in the way that each of these tags are associated with detection names. But on the other hand, they are non-exclusive, whereas detection names are exclusive, and you can only tag a sample with one detection name. Here we have these non-exclusive descriptions that are higher level and that we can effectively use to try to learn with a neural network. So we moved from a bunch of data that we had in detection names into something that we can frame into a multi-level machine learning problem. And this is, again, the process from going from detection names to tags. We first extract all the tokens through some parsing, and then associate those tokens, look at if there are any tokens that we have associated manually with the tags. There is some other boilerplate and statistical enhancements for how we develop the tags. I'm not going to get into that right now. But with this in mind, we created a data set of 10 million samples, a larger data set of 76 million samples, and 2 validation sets that we've split 1 year for the training set, 1 month for validation, and for deciding which kind of models we want to move to the test set, and a test set that also contains 1 month worth of data. We extracted features directly from the binaries. We use the 2-dimensional binary entropy features used by Sachs and Berlin 2015, which contains information about the p header, the import table, the printable strings that are contained in the p file, and entropy statistics about the p file that turn any binary into a 1024-dimensional representation. And we use these labels that I just showed you that were extracted from detection names from these 10 different anti-malware solutions that we know they're well known for generating fairly good detection names. This is how the dataset looks like. We have about 30% of our samples are tagged as packed, and about the same amount are spyware. We have 8% of those are ransomware, over 2% are crypto miners, and the chart that we are looking at the right hand of the screen is the empirical conditional probability of the tag in the y-axis, condition on the tag in the x-axis. So this is to have a feeling of how our labels are distributed. So in order to try to learn from this, we tried different methods and different neural networks. Out of the results on the validation set, we found out that there are 2 networks that stand apart that produce the best results. One is a very simple feed-forward neural networks with 11 output nodes, one of each representing the tags that we're trying to learn. It's worth noticing that even though we've defined 11 tags and that those tags with those tags, we know that we cover 96% of the samples in our training sets are tagged with at least one of those. But it's not necessarily the case. We could have used 15 tags, 20 tags, 5 tags. It's not relevant to the method. One thing to take into account about this network is that the best results were obtained when we do this thing of moving from the 1024 dimensional representation, explode the representational space to 2048, and then go down to 128 and back down to 11 tags. The output, the predictions for each of the tags can be calibrated independently, and we have a sigmoid nonlinearity for each of the output nodes to get the predictions. Yes, Haram?
Input size of the binary?
So we are using this input representation of 1024 dimensions based on the two-dimensional byte entropy features by Sachs and Bradley, similar to the ones used at Ember. The second model that we tried, and the one that ended up producing not only the best results, but also the most interpretable ones, is a joint embedding model. This is something fairly standard in the computer vision area and computer vision field. It's composed by 3 different parts. The first one, we call it the p-embedding part, which transforms the initial feature representation of 1024 features into a 32-dimensional representation in this embedding space. Again, the best models go first up to a representation of 2048 and then go down. And yeah, we have a second component, which is the tag embedding component. So we also get each of the tags that we are trying to learn and run them through an embedding matrix and obtain a 32-dimensional representation of each of those tags. And then, since we have both executable files and tags in the same space, we can simply measure the distance between the embedding of the executable file, represented by H in the diagram, compare the distance with the embedding representation of the tag, represented with E, and get a prediction depending on how close those are in the embedding space. In practice, we used as a distance a dot product. We also experimented with different types of distance. This is mathematically similar to the previous model, but it has certain advantages that we're going to see. And the other practical thing to take into account is that we constrain the size of the embedding vectors, so they have L2 norm of 1 in the embedding space. The idea behind this is that we have the explicit ability to model the relationships between our labels or our tags. So we're not only looking at the relationship between files and tags, but also looking at the relationships between tags themselves. This is how the results look like in the test set. So this is 1 month after training our model. Overall, and I'm not going to get into detail about too many details about the results, but these are what we're measuring as our main metric is true positive rate. This is because when we extract the tags and we create our labels, we have this positive relationship between samples and tags, but the converse is not necessarily true. If one tag is not present, it doesn't necessarily mean that the sample was not related with that tag, but it was not identified by the vendors as related with that tag. Overall, the performance goes up to 90% for a false positive rate of 1%, with the notable cases that ransomware, cryptominer, Floater, and file infector perform really well and way better than the rest of the tags. This is a per tag evaluation. If we think about how many samples we are getting right, for 71% of samples, we are able to predict all the tags positive and negative tags per sample. So for 70% of the samples, we get all the tags right. Why are we interested in this and why we think this is useful? It helps us to generate contextual information about the samples that we are detecting in the wild. So if we are doing any type of layer detection, we have this piece of information that tells us automatically this is, for example, a downloader. So that's already a piece of information that might makes us look more closely into the network connections that this file is going to make. Or if it's ransomware, it also gives us this context to further analyze how the behavior of the sample executes in the wild, as well as if we are in a SOC context, Security Operations Center context, it also helps us reason about the kind of things that we encountered, and helps us also go back and try to understand how the attack was performed. It is helpful to prioritize a long list of events. So if we are in a Security Operations Center case, and we are receiving alerts and hundreds of alerts per hour, then it's not the same as if something was identified or thought as ransomware than if something was identified as adware. So it gives us this very easy way to prioritize and order events in terms of how critical they might be. And also, and this is not something about the approach itself, but about having this description framework, is that gives us a common way to reason about malware within in our case, within Sophos, but in the larger organization. So if we have different ways of detecting malware, having a common way of describing them, it's useful to share information about different components. So if our dynamic behavior engine generates the same kind of descriptions that our machine learning model is expecting to learn, then there is lots of reuse and knowledge reuse in that sense. Finally, we have shown in previous research that learning these tags at the same time that we're trying to learn a binary malware benign classifier, it helps in boosting the performance of the malware benign classifier just by trying to fit as well and to learn these tags. So that's an additional benefit of doing this tagging. Going back to why we think the embedding space it's useful, it's very easy to inspect. So by just looking at the representation in these 32 dimensions, we can easily visualize how samples relate to each other. So what we're looking at here is a t-SNE representation of both tags and malware samples. The large markers correspond to tags and the small markers correspond to samples. So we see that effectively we are learning a representation space that makes sense and things cluster together. This is 750 different samples that were tagged with only one tag. Finally, going back to our original question, are we really learning things about are we really capturing this knowledge that the reverse engineers and the malware analysts put when they wrote the initial signatures? We ran this experiment in which we brought samples from our test set that we know which families they belong because we have a dynamic analysis in place. So we know for sure that these samples come from these 12 very well-known malware families. And then we can not only measure in the embedding space the similarity between a sample and each of the tags, but we also can measure the similarities between two samples themselves. So from these 12 families that we have, we took one anchor out. So we have one representative for each of the families. We are left with 1,500 samples that we don't know to which family they correspond. If we just look at which is the anchor, the nearest anchor in this embedding space, we are able to guess with very high accuracy which was the malware family that the sample belonged originally. And this is something that works way better in this joint embedding space compared to hidden representation from the feed-forward network, or compared to similarity metrics out of the initial 1024 features. For example, with one anchor, we can predict emotet with 90% of true positive rate, Apache with 91%, and QQPass with 74%. And these are all families that are within the same spyware category. So it's like we can zoom in one of these tags and still have the ability to differentiate from which of the families they correspond. And that's it. This is the preprint of the research that we've done. It's available on archive. And yeah, it's still research in progress that we're hoping to get published sometime soon. Yes?
Yeah. Are you working with...
We've got a microphone for this. For the people at home. Oh, we've got a microphone runner. Cool.
Yeah, are you working with unpacked binaries before you classify them, or do you have some sort of an unpacker? If you're working with packed binaries, have you figured out any insights as to how the heck this is even working to be able to come up with these insights?
So here we're only looking at the binary representation of the file as it comes. We don't do any unpacking. And one of the tags that we are predicting is actually if this malware sample is packed or not, whether it's packed or not. So that information could be, again, going back to this idea of layer detection, just having a very accurate prediction of whether a sample is packed or not can help us trigger different unpacking mechanisms while the file is executing. Welcome.
Thank you so much for the presentation. So one question that I'm curious about, since all of this is supervised to some extent, have you compared or considered something that is unsupervised, like for example, like topic modeling from NLP? Something similar to that, where you can try to discover distributions of different topics within all of those binaries?
We try to frame it in that sense. It's a line of research that we didn't follow, but yeah, at some point we were directly parsing the strings of the family names and trying to learn which was the important bits of information that we could extract and then use as tags. We looked a lot at relationship between the tokens to make sense if one token, for example, you might have a token that's WannaCry, and then you have another token that it's ransomware. So trying to exploit the fact that there's a hierarchy, a very clear hierarchy within those. It's not something that we've applied to this particular line of research, but this zooming in and being able to have a hierarchy of tags, it's something that, yeah, it's definitely worth exploring and would be unsupervised.
Thanks for a very nice talk. Can I ask two quick questions, not very conceptual ones? On this slide here, I think you said you prefer TPR as a metric to AUC. Does that make a big difference?
I mean, we look here. I had to put one plot. I decided to put TPR. We look at AUC, so that's the mean AUC across the tags. It's 99. We use different metrics, and we try to globally optimize for all of them. TPR is the most relevant because of how we do the process of extracting the tags. In this case, for example, let's say the one at the top, maybe none of the security vendors we got the detection names from identified it as packed, but that doesn't mean that the sample might have been packed anyways. So because of this very accurate positive relationship between labels and samples, but not necessarily negative relationships are not as strong, that's why we think of true positive rate as the leading metric when evaluating success.
Thank you. Can I ask one more quick one? I think on about slide 14, there, you've got, it'll just clarify things for many of the slides that came on. Could you just say again what you thought about the labels from tag, data-driven augmentation of tag, token to tag mapping?
Yes, so this process of parsing tokens out of detection names and then converting them into tags, there is a manual process that we actually worked alongside with malware researchers to associate tokens to tags, but then there is a process in which we looked at statistical relationships between tokens and tags, so we can detect tags that maybe Sophos calls it in one way, but then Kaspersky calls it in a different way. So identifying these siblings relationships and parent-to-child relationships helps us augment this mapping from tokens to tags. That's what it means with data-driven augmentation. And again, in the paper, there are further details about how that's being done.
Thanks for the great talk. I just have a question around productizing. Have you guys considered delivering the tokens to tag or the name to tag feed as a thread feed, similar to an FSISAC or something like that? So
similar to?
So you could subscribe to a feed of like malware name to tag to be consumed by, say, a SIM or an EDR platform, similar to an FSISAC feed or something like that.
So the prioritization part, we are still working on that. Ideally, and the most simple scenario is to have a thread score associated with each of the tags and then find a good way of combining those so we have a thread score for a given sample. This is part of a larger endeavor on working with endpoint detection and response teams and finding out what works also best for them. So it.
More about integrating with Sophos, your platform.
So just to help that answer your question. So Sophos is coming.
Konstantin is my boss here.
Just to do a little marketing, I guess. Like Sophos coming up with I think we call it Untitled platform, where you're able to submit files to our platform, and in the background, all our machine learning models we expose them, and you can get feedback. And at some point, we're going to put the tagging model in there, so you can submit the file and get the tags from that, even though there are no vendor labels or anything.
Please summarize that for our streaming audience.
Actually, slight chat privilege. This would be really bloody useful for the ISAPs.
So yeah, we are going in the near future. We're going to expose, or we're working in exposing all our machine learning models into the cloud, so people can submit samples and get results from analysis from different kinds of models. The tagging model it's one of those, one of the models that is going to be built into that field.
So you had, can you hear me? On the bar chart where you were showing the accuracy, the downloaded ones for some reason didn't work as well, and you were saying how joint embedding was a pretty explainable model, so I was curious if you dug into why it didn't work as well for those. Is it just less representation in the training set or something else? Maybe it's in the paper, I don't know.
Yes, it's not very well defined, basically. It's what we ended up finding is like too broad of a description of what we were trying to get at. And there is lots of label noise in samples that we know there are downloaders, but it's not showing up in our labeling mechanism, or the other way around. So yes, that's it. Just to clarify on this slide, the one that is performing the best, the orange one, is the joint embedding model trained in the larger scale, 76 million data points.
I think
just one more question and then the next.
Hey, nice presentation. Quick question. So on your confusion matrix, I see it's quite sparse and you see a lot of false positives. So just wanted to ask if at all you are taking the input from these false positive, reinforcing the learning and then somehow improving your tags?
So you're referring to this slide,
yeah,
right?
Yeah.
So this is not a confusion matrix. It's what we're plotting here is the conditional probability of one tag given the other. So for example, with the first row, the probability of adware given, let's say, installer is 68%. And that comes straight from an inspection on the dataset. One thing that we do, nevertheless, is to compare this matrix with the one that we obtain from our predictions. And that's where we can see mismatches and see, oh, there is lots of ransomware that is actually being, the probability of ransomware given installer, let's say, is way higher in our predictions than in our training set. So that's, one source of information to help us look deeper into our labeling procedure, definitely. Right, thank you very much.
Thank you.